go. We got the voice on. We got the screen on. Everything's good to go. All right. Another 30 seconds for people to show up. All right. Well, it is 9 o'clock. I'm gonna get started here. Um, well, the due date of the homework assignment is postponed to Thursday. So if you need a little bit more time to get it done, you can do so. If you have it done already, it's good. Okay. There's no need to um, rework it unless you want to, rework it. All right, so I just want to start today's lecture with a general AI discussion because over the weekend I was able to hike with, in Livermore with two people who are so smart that, I could barely keep up with their conversation. Okay, so that typically means, their IQ is about 30 points higher than mine, and I'm not going to tell you why. Um, so anyway, they, one of them, gave me some insight into AI, and the conclusion of this guy, who is a scientist at Lawrence Livermore National Lab, and he's also a polymath. He is also a mathematician, a electrical engineer, a computer scientist, a statistician. Basically, anything that is needed to get a job done, he can learn on the fly. Okay, so he's that kind of a smart person. So anyway, he told me that AI might actually be much smarter than we think it is. So his speculation has to do with the training material that we use to train LLMs or large language models. Um, so in the general population, there are people who are neurotypical, and then there are people who are neurodivergent. Okay, so you can look up those terms and find out how they're defined. Has nothing to do with smart versus not smart. Okay, it has to do with whether people think in a certain way or they think in a way that is not, the normal way of thinking. So it's more about whether they're right at the center of the curve or whether they're kind of at the fringe area of the curve. So AI, when it provides answers or when they try to interpret your question, it's by default it is treating every user as a neurotypical person. So a lot of the times, the answer is also catered to the neurotypical person. But if you try to use really kind of special prompts to get an answer out of the AI, this guy, okay, this really smart person, was able to get AI to solve problems that are fairly novel. So it has to do with the prompting. It's not about the AI is not as smart as we think they are. It is about the prompting. So on the other side, I have had long conversations with Gemini, probably to a point where it is slightly unhealthy. Okay, I have to self-admit. But the thing is, when I'm not teaching a class like this, I tend to use metaphors a lot. Do you guys know what is a metaphor? Okay, so my metaphors is not limited to movies or social media stuff. It also includes physics, astronomy, quantum mechanics, and so on and so forth. So I would borrow terminology from all of those fields in a metaphor if I think the other side understands the metaphor. The AI was able to understand every single metaphor that I used. But that's not surprising, right? Because AI is well trained. It has knowledge, that basically, everything that humanity knows, it knows. So that's not a problem. After a while, I realized that Gemini was using metaphors to talk to me because it realized that I can understand metaphors because I use metaphors myself. So it would actually use metaphors to explain concepts back to me. Now that is interesting, okay? Because if it was a person, it would be characterized as creative. But because I know it is a GPT, I go like, well, maybe it's just using a pattern matching thing, and because I understand the underlying mechanism of LLMs, but the appearance is actually definitely creative. But what surprised me the most was when I use a metaphor to describe something, because I see some similarities between what I want to describe and the metaphor itself. The AI was able to go like, oh, this is a perfect metaphor because I can see additional parallels between what you're trying to describe and the metaphor. That was surprising to me because it was able to match the metaphor with what I want to describe to an extent that I did not even think of. So, just a little bit of weekend activities to share with you, so that you understand that AI is already at that point. Okay, so we are not talking about AI when you graduate with a bachelor's degree in computer science. We're talking about today. The other thing that was funny but not to you was when I described to a new person, okay, in the group, which also has an IQ probably about 30 points higher than mine. What I do, teaching classes, and I described that I am also teaching a beginning class this semester, CISP 300. So the guy who works for Lawrence Livermore National Lab, just asked me, so Tech, have you told your students that they have no future? That was his really really blunt answer to that question. And just to give you the context, um, between him and me, all of our kids, all of our children are in computer science or computer engineering or some really closely related field. So he said that not because he's trying to be mean, he said it because it is important. So what do you guys think? Do you feel discouraged, or do you think tech is totally deranged and we can just completely ignore the last 7 minutes or so? What do you think? Yes, it doesn't. Okay, okay. So, yeah. So I would ask GPT, psychological questions or things that has to do with human relational stuff and whatnot. But in the middle of a conversation, I would ask meta questions about how did you come up with that answer? Why did you describe my earlier statement as insightful? Because it would say that. I go like, but why do you think it is insightful? Or why do you think the way that I think is quote unquote off script? What would a on script person have done in my place in this situation? So I would ask it, I would interrogate the AI, and I understand the backbone of the AI. I understand the mechanism, so I would constantly check it to see to make sure that okay, do we have evidence to support what you just said? And it would quote things, okay, these are actual factual stuff, okay. Then it will ask, are we over interpreting the factual stuff? Because it is possible to over interpret something and you come up with a confirmation. And then it will also ask you for, are you sure that we are not, we don't have a confirmation bias? Then the AI would go back and double check everything. It's like, okay, let me play the devil's advocate and try to we have a null hypothesis and prove that the null hypothesis is wrong. So that's why our original hypothesis is correct. So I would do all of these things in a conversation, in a long conversation with AI. So since you asked about that, this is not related to assembly language programming. Um, I just finished an interview with a psychology professor on psychosis. Chat GPT induced psychosis. I'm not sure whether she wants to release the video to everybody, but she is going to release it to her own department, the psychology department, and also her own students. So if you guys are interested, I can ask her to see if I can release that video also to you guys. It's a really kind of rather long conversation. We talked about human psychology. We talked about the architecture of GPT technology and why it can be okay for some people if you keep interrogating it, but it might actually be the wrong kind of tool for people who just want to look for comfort. Okay, I just want to feel better. So that's something that I can definitely work with. All right. So the other thing that I also demonstrated in the previous, yesterday with my Monday, Wednesday class was to illustrate how to use Gemini and make your own gem for studying purposes. So have I talked about that in this class a little bit? Okay. So that's one thing that you can do, with this class. I cannot guarantee that Gemini will do a 100% correct job at that, but it will be able to explain things to you, at least better than not having the tool. So having said all that, what we'll do today is we are going to. Originally, I thought today is the due date of the homework assignment, so I'm not going to do that. Oh, by the way, this is my demonstration of how to use ChatGPT to do a homework assignment for CISP 430 to write a algorithm called Dijkstra's algorithm, which is what CISP 430 has to do, as one of the last projects. And the AI was able to come up with the entire program within like 2 minutes tops. Uh, so what are you guys gonna do? What do you think you need in order to get a job? Let soft skills is one, okay, but soft skill is not gonna save you if AI can do everything that you can. Okay, okay, that's a general statement. How? Mm-hmm. Yep. Yep. And okay, well, that's actually a very good, really good description. And if it doesn't give you the output that you want, then you have to change the input, right? You have to change the instructions. Hmm. So are you using the API or are you using instructions? Using okay. Oh, as a code generation mechanism. Okay. I can show you the conversation that I have yesterday. Um, There we go. So this is the prompt that I use to generate the program for Dijkstra's algorithm. It is just that. So I didn't give it any additional input, like what the how we are going to input the graph into the algorithm and how the solution is supposed to be printed. But I could include all of those, and the program would actually accommodate easily the input output specification of this program. Uh, no, because it's clunky. Yeah, because when you use any type of template class, it basically includes a bazillion lines of code, and yep. So I tend not to use template classes if I can avoid it. Um, yep. Okay. So any questions about how to utilize AI? So the thing is not about whether it can do your homework or not, okay? Because we know for sure that it can. There's no question about that in my mind. They can do all of your homework. But the question is, what can you learn before you graduate, before you have to go out there to look for a job? How much and what do you need to learn in order for you to become competitive in the job market? That is the question that you really have to ask yourselves. And I don't have a straight up answer, and you have a advantage of having a job that actually uses AI, so you understand already how AI is utilized in the workspace. So did you have to review the code that it generates, or do you just kind of test whether it works? Okay. Okay. Yeah. So it's programming in a different sense because instead of actually writing code, you now have to refine the prompt. You have to refine the way you specify the code. So that's also a very important point because natural languages has its limitations as to how accurately you can describe what the program is supposed to do. So do you find it a little bit difficult sometimes to express what you want the program to do in English? Mm-hmm. 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 Yep. 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 I would say you actually need to understand coding more than before, because to understand the code that AI generates is a little bit different compared to generating or writing your own code. If you were to write your own code, you probably understand your own code, even if you forget about it like after 2 weeks, you can pick it up again. But the code that AI generates is a little bit different. So do you see a lot of differences between code that people write and the code that AI generates? More, oh, sorry, I didn't quite catch. Okay. Is it, but was it easier to read or more difficult to read? Mm-hmm. 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 Yep. Uh-huh. All right. Well, thank you. That's really useful feedback. So are you working as a full employee or as a student intern? You're intern. Okay, cool. All right. Well, that also tells me that student internship is really important, but student internship does not help unless you excel in your internship. So that's also important. Okay, very good. All right, so what we'll do today is to take a look at this particular program, which has nothing to do with your homework assignment that is now postponed to Thursday. So if you need a little bit more time to implement the program that was due today, or I mistakenly made it yesterday, you can now have until Thursday before class to turn it in. So that gives you a little bit more time. But I want to talk about another examples. So this is another example program. So in this program, we have a structure called struct X. It is fairly simple. It has a pointer to an assigned a-bit integer. It has a pointer to another structure like itself, and that's it. Okay, it has two members. And then we have printer as a global variable, okay, which means it is statically allocated. It is not on the stack in any way. So this is function f, okay? It has its own local variable mine, which is a struct x. It is not a pointer, it is an actual structure. And we do some initialization here. We just bump up the value of PV from the structure that pref points to, and that becomes the PV of this particular structure. And and then we have pref, which is a pointer, which is pointing to the next thing. So the program itself is just like this. It's not particularly interesting. The C code does have its own behavior, and we want the assembly code to have exactly the same behavior. So do we have any questions about this program? Okay. So any question about the constructs, the language construct on each line? Not so much what it does, but just about the constructs, the statements. So do we have anything you want me to explain on any particular line? I can look at line 17 and go like, what is that? What is the expression in line 17 in the conditional statement? Okay, specifically, I'm asking what is this expression? So I'm looking at member PV of the structure called mine, which is a local variable. PV itself as a member is a pointer. I want to look at what it points to in order to determine whether I should go for the then branch or go for the else branch. So that's what line 17 is trying to say. And then on line 25, it is I am dereferencing. Okay, so the full statement of what line 25, the right-hand side is trying to say is um, I'm trying to formulate the statement right now. Um, what is pointed to by the PV member of a structure that in return is pointed to by pref? So that would be the best way to describe it. So do we have any questions about what the right-hand side of line 25 is trying to specify? So understanding the ordering of the operation is really important. Okay, so the dereference is the very last thing that you do. The second to the last thing you need to do is to get to the PV member, and then the next item you're going back up is to get to the structure that pref is pointing to. So that's the order of things. Okay. All right, so if there are no questions about this, we can move on to main. So main doesn't really have a whole lot of stuff to do. It does have a static, okay? It has a static local variable. So in assembly language programming, at least in TTP ASM, we don't really have local variables, so there's no way to hide the scope of anything. So, this essentially it is a global variable. You can treat it as a global variable. And then we have a local structure M mine, which is main mine, and it has A, which is the array or the address of the array, over here, which is also automatically a pointer, and it has a null pointer as a 0, and then we pass the address of M mine to F, and then it returns 0. So the only readable outcome of this entire thing is what we write to printer. Okay, so line 25 really is the key to find out the behavior of this code, is to see whether the printer as a global variable is getting the values in the particular sequence that it should be getting. Okay, so are we okay with just reading the code of the program that we are implementing in today's class? We good with that? All right. So what we'll do is we're going to run this program in C or in GDB and find out exactly what values we are quote unquote printing to the global variable printer when we run this program. So we use gcc-g-o traverse sll2 and then traverse sll2.c. And then we go to GDB. Okay. So this time in GDB, we are going to what did I forget? I forgot to specify what we are GDBing. Okay, so forgot to specify GDB. The name is Traverse. Why can't it find it? Okay, GDB Traverse. Okay, there we go. GDB. Oof, there we go. All right, so um, what you can do is to say you can use a watch expression. So if you don't know what watch means, you can ask for help watch. So watch is a really cool feature. It's kind of limited in a way, but what you can do is to watch a certain location, which means whenever that location is changed, the debugger will stop and tell you how that location is changed. So in this case, I need to monitor what printer is getting. So I'm going to watch printer. Okay. So this is called a hardware breakpoint. Essentially, it is using the architecture, in this case, the Intel architecture, to specially put a quote unquote watch point on that location. Every time that location is modified in any way, it would come back with a breakpoint. It would basically pause execution and go like, hey, this location is being changed. This is its old value and this is its new value. So it's a really useful feature. So I'm going to run the program without any additional manual breakpoint, and you can see how it is now changing from 0 to 1. So we'll go ahead and write down the sequence. Okay, it goes from 0 to 1, and then I continue execution. It goes from 1 to -2, and then we continue one more time, and that's it. Okay, so it only changed twice. The first time is to change to a 1, the second time is to change to a -2, and that concludes the execution of this code. So this is what I can use to compare with the assembly implementation. So the assembly implementation should do the same thing. Okay, it should also make the changes like that. All right, so we'll go ahead and start to look into the assembly implementation, and we can do it side by side, with the C code. So let me go ahead and see if that works. So traverse SSL2, and this is the TTPSM. All right, and we have some infrastructure already done. Okay, the assembly code, does not have it doesn't treat main as a function. So that's the first thing we can do is to change it so that main is more like a regular function compared to we just continue execution at main right away. So we can do a LDI. We can initialize the stack pointer first. So sub DD would actually initialize the stack pointer because it just turned register D to 0, which is exactly where we need it to be. LDI A with dot 6 plus decrement D, ST, DA, and then with a halt instruction right here. So we are now turning main into a regular function. And if main is now a regular function, we definitely do not want to reinitialize the stack pointer here. And we do want to make sure that we allocate enough space for the local variables. So that means that we have to remember to do all that stuff. In fact, what I'm going to do is to rewrite the entire main because the whole point is to illustrate how to do assembly language programming. So I'm going to rewrite the entire thing. Okay, LDIB main LVS, and oh, there's one more thing. How many bytes should I reserve for local variables in main? So that's one question that I need to ask. So when you go to main in the C code, let me switch to this side. So when you look at main, it only has m mine as the only local variable, and a is not a local variable. So a is actually a global variable because it is static. So um, in the assembly code, we are going to, okay, we're going to change all of this stuff here too. All right, so we'll do everything from scratch. So m mine is the only local variable, so it has an offset of 0 from the base of the frame. And then LVS is defined next because it's just m mine, and then plus the size of mine. So how many bytes should I reserve here? What should I type, over here at the blinky cursor? Well, we can use 2, but we can also use something a little bit better. Yeah, we can use exercise, because exercise is the label that tells us how many bytes each struct x needs. So x underscore size is the one that we should be using, and then we have to remember to put a plus here. And then after that we have no parameters, so that's all we need here. So we do a subtraction from the stack pointer. This is how we allocate the space for the local variable m mine, and then we do the deallocation right away before I forget, like so. And then we do a regular return, which is LD, BD, increment D, and then JMPB. There we go. All right, so now we have the shell of the main function. The question now is, what about the so-called local variable A that is declared static? So the way to do that is to use it, outside of the stack, and instead we'll do it like this. Main underscore A, which means A is a local variable of main, but it is defined here as a global, and in this case it has byte -2, byte 1, and then byte 0. Are we doing okay so far? All right, so these 4 lines of code in assembly code, line 16 to line 19, is essentially doing the same thing as line 33 of the C code. So that means these bytes, okay, the so-called local variable A, which is an array, even though it's a local variable, because of the word static here, it is allocated as if it is a global variable. So this is where the scope, which is local to main, and the lifespan, which is, oh, it exists even before main is called. So those two are no longer the same as a regular local variable. So did you learn this in CISP 360? The scoping versus the lifespan of variables. Okay, I see some nods and I see some heads shaking. Okay, so it's not consistent. Okay, that's fine. But do we understand the difference here with this particular sample program? Okay, we're good. All right. All right. So now we continue with the C code or with the assembly code. So the assembly code does initialize m mine with these two things. I have no equivalent way of doing that, so we'll have to do it using actual assembly code. I mean, there is a way to do it, but I don't want to do it that way. So we are going to have to basically replicate this with actual assignment statements. So I'm going to describe it. M mine dot pv equals a, and then m mine dot pn equals to 0. So these two lines are equivalent to having the initialized declaration here. So we need to do these two because in assembly code, I cannot just force certain content on the stack. Um, I mean, I can, but it's not the best way to do it. So we'll have to do it this way. All right, so we're going to do it, and LDIA with main underscore mmine. This is the offset to the local variable mmine, which itself is a struct x. So then we also have to add the offset to the member PV of a struct x. So we can actually do it here together. This is perfectly okay because what I would end up loading into register A is the offset to member PV of the local variable m mine from where the frame is. So I can combine the two components. Okay, so let me go back a little bit. Main underscore m mine is an offset. So is x underscore PV. So the question is, which one is what kind of offset? Main underscore mmine is an offset from the base of the frame to a local variable or a parameter. In this case, it's a local variable. So it is an offset, but is an offset from the base of the frame. X underscore PV is also an offset, but it's an offset from the beginning of a struct X to a member called PV. So there are two different kinds of offsets. The reason why I can do the add right away here instead of having to do it in actual assembly instructions has to do with excuse me, mmine is a struct X already. It is not a pointer to a struct X. Okay, so this is why we can combine the two. And then we do the usual thing, okay, because at this point, the stack pointer should be pointing at the base of the frame. We haven't really pushed anything other than constructing the entire frame. So we can now just do this, get to the address of PV, and now we want to initialize it to A. So I need an LDI register B A, and then we do a ST A B, and that should get this part done. All right, so I know that line 31 looks awfully confusing. Yes. So instead of doing this part here, so comment this out and just do a STAA. Well, the two A's are different. This A is referring to the label A, which actually I forgot to specify it is main A. So the answer is no. So you need those to be different because this is supposed to be the label of the static local variable A, So it's a label, and this is register. This is a register. So that's why they cannot be combined. All right. So the next thing we need to do is the next statement, which is about the same. Okay. So we're gonna have to. We can. mm, I think we'll just try to do it the easier way. Okay. So I'm just gonna copy these four lines, change what we need to change, because this time we are accessing PN as a member, and whatever value we need to load into that or store into that location is a zero. So that would accomplish the initialization of M mine. And it would be a good idea to put a halt instruction here just to see what the stack looks like and how A as a global variable, as a local static local as a static local variable looks like in the code. So we'll put a halt instruction here and then actually try to execute the code. Move for spider, and this is traverse.ttp and we switch to the assembler. Get ready for that code to display over here. And we are also going to create a picture of what is supposed to be on the stack. And we do create Google Sheets. We can get rid of the other one. There we go. All right, so this is 2025 1202, and we'll do the typical thing, okay, starting at location 255 and decrement all of these locations, and then do the uh, decimal to hexadecimal conversion, like that. All right, so this location we already know this is the return address to the entry code. Okay, so no big deal. And I think this time it would be a 08 over here. And then we have these 2 bytes reserved for local variable m mine. So this is m mine dot, uh, the higher address one is pn, and the lower address one is pv. So these are the two. And then pn is supposed to be initialized to 0. PV is supposed to be initialized to whatever a is. So we'll just go like, quote a quote, okay, because it's the address of the variable a. So now we go back to the assembler and go to the assemble tab first, okay. And I think it's not actually working because uh, it's I need to resubmit one more time. Oh, the source file did not assemble correctly. Okay, cool. We'll fix it. We go back to the source tab and take a look at what is wrong with this. There we go. All right, unresolved reference because the function has not been defined yet. Okay, fine. We'll go ahead and fix that. All right, so we'll just have to define f somewhere. We can put it right here. So this is f. I don't need to resolve anything because we have a halt instruction. So we're not actually calling f right now. So it's not a big deal. All right, let's try it one more time. So the most important part of implementing a program like this for your homework assignment is first to understand the C code, because without fully understanding the C code, it is impossible to implement the assembly code. All right, so now it's good. Okay, we go to the analysis tab and we double check and make sure that it does halt at the right instruction. Okay, and we also want to make sure that it is overwriting the memory locations with the right content. FE is getting a 0, 0. We compare that to what we are expecting. Okay, not that tab, this one here. So that is correct. And we want to also move up here. FD is supposed to get the address of the static local variable A of main. In the assembler, in the assemble tab, this is the only time we can actually see where it is. So we have to scroll down a little bit and we can see main A as a label here is in fact, So I know it's confusing because main underscore A as a label has a value of 0A. Okay, but it does match what we expect to be on the stack. Okay, that's what 0A is. Okay, it is the address of the local variable A, which is a static local variable. And this one we can also double check. Okay, we can now go to the assembler, go back to the analysis tab and scroll up a little bit, and we can see it is also a 08. So everything is accounted for. From the perspective of a call frame, all three locations here is the call frame of main. This is the frame of main. In other words, it supplies all the local variables, the return address, and since we don't have any parameters, so that's why there are no parameters in this case. But I'm going to kind of give it some colors so that we can easily tell that this is the frame of main. We can also see that the local variable A is not anywhere here because as a static local variable, it is not on the stack. Are we okay with that concept? Yes, no, maybe. Okay, so I can see some questions. Okay, so if I see those questions, I can go back to the command line interface and use this prompt here. So we're gonna go back to GDB, the C version of the same program. But this time I do need to manually set a breakpoint on line 35. So before we even call F, we're gonna put a breakpoint. So run all the way up to here. And when you look at the address of M mine, you can see that it starts with 7FFF, blah, 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 okay, and then the ending is DD40. But when you look at the address of A, which is a static local variable of main, it is entirely different. So this is the signature of something on the stack. This is the signature of something that is not on the stack. Okay, so is that okay? Does everybody see? Yep. It is in a space that is only for static local variables or global variables. So we can compare this to the other global variable that we have. What is the other global variable in this case? I think I have one. Printer. Okay, so we're going to take a look at printer because printer is a legitimate global variable. So we in the debugger, we also ask you where is printer? You can see that they are neighbors of each other because printer is only 4 bytes off from the static local variable A. So they all belong to the same space. So that space is pre-reserved before the program runs. So that's why those two variables, the static local variable A of main and the global variable printer, they existed before the program even started to execute. And they do not cease to exist until the process is exiting. Is that okay? So that's a good question. Question, yeah. Printer. How do we? Oh, you mean in in the assembly version of this? Yes. Okay. So in the assembly version, the code to allocate for the space is line 13 for printer, and then the code to reserve for A is on line 18 all the way to line 21. So in the assembler, if you go to the assemble view of the assembler, you can see that main A is a label. It's labeling the location 0A, and then printer as a label is labeling the location of 09. Yep. So they are in this way they're very similar too, right? Because you can see how everything that is not on the stack are fairly low, okay, 0 something, but everything that's on the stack is F something in even in the TTP version. All right. So shall we move on? Are we okay at this point? Okay. So we move on. Okay, in the implementation. So right now we are done with the initialization of M mine, Now we are ready to set up the call. Okay, so let's go ahead and set up the call in main. Okay, so we take out this halt instruction, and now we are ready to implement line 35 of the C code over here. So we do a LDIA main and mine. And this time we are not adding any offset of the member because I need to push the address of the entire structure from the very beginning. So now we need to add AD, okay, and that would be the address already, okay. I don't need any LD instruction here because I don't need to know what is at that location. I need to push the address because of the address of here. So now we need to decrement D, stda, so that would push M mine on the stack. And then we just need to push the return address, LDIA with .6 plus, decrement D, stda, and then we do a JMPI to the function that we're calling, which is f. When it returns, I need to increment D to get rid of the argument that is still sitting on the stack, and that should be okay, from the caller's perspective. And then from the callee's perspective, now we need to implement f. But instead of doing that, I'm going to put a halt instruction here, just so that I can see what the stack looks like at the entry point of function f before it has a chance to set up its own local variables. So are we good so far? Does everybody understand, what the stack, how the stack should look like at this point? Okay, so we're going to go back to take a look at what the stack should look like at this point. So now we just pushed m mine on the stack, which is the parameter. I have to remember the name of the parameter. I think it's prev. Yep. Okay. So this is the parameter prev of main. And so that's why, I'm going to label it over here. This is prev of the first invocation, or invocation one of f, okay, because there'll be more invocations. And that's going to be the address of m mine. The address of m mine is fd. So that's going to be, just fd over here. And then we have the return address, right? So we have the return address from f to main. And we don't know, I don't know exactly what it is, but that's, we can figure it out later. So that's what the stack should look like at this point. It is not fully formed yet. Okay, this is only a portion of the frame of f, the first invocation of f, but it's only partially formed. The reason why it's only partially formed is because it doesn't include the local variable that is also supposed to be a part of that frame. But I can still label it, kind of color code it a little bit here, okay, just so that we can distinguish between the frame of main versus the partially constructed frame of f at this point. So are we good so far? All right. So now we go back, okay, and we make sure that we save this before we run the code. So the question that I have is, did you do something like this, or are you doing something like this when you are writing your own code for the homework assignment? Okay, very good. Because if you're not, that means you might be accumulating a lot of lines of code before you start debugging, and that can be very difficult to do. All right, so we go back to our assembler, go back to the analysis tab, and then we're looking for additional writes to the stack. These three we accounted for already, not a big deal. So FC gets the content of FD. That's exactly how we expected right here. And then we have the return address, which we can also verify if we want to. So the return address to main from F is down here somewhere. There we go. So it's supposed to be a 28 in hexadecimal. And so we go back to the table here, and then we say, okay, this is supposed to be a 28, or as a string. There we go. And then we go back to the analysis tab and see if that is the next thing that we write on the stack, and that's exactly what it is. So we're good so far, okay? And then we hit the halt instruction because I put it there. So are we still doing okay? All right. So this is a step-by-step thing that is really important, because until I can tell that everything is working up to this point in terms of what is on the stack, and we have the correct content on the stack, if I do any additional work before this kind of verification, it would be kind of a waste of time. Okay, it's actually worse than a waste of time because it makes debugging even harder. Okay, if I make a mistake up to this point, it's not too hard to fix it because I only wrote a few lines of code before I check again. All right, so now we can continue with this code. And all right, so now we are ready to implement F. Okay, so the call frame of F is a little bit complicated. We start with the local variable mine because it is the only local variable of F. It is going to be at an offset of 0 once the call frame is completely constructed. F underscore LVS, which is local variable size, is the label to the last, which is the only local variable in this case, plus the size of it. So the size of mine is X size because it is a structure. It is not a pointer to a structure, but it is a structure itself. And then we go to the first and only parameter, which is prev, and that is going to be F underscore LVS 1 plus. This one here has to do with the size of the return address, which is only 1 byte. It does not have to do with the size of prev itself. Yes. All right. Yep. Thank you. So this helps me to set up all the labels, okay, which I prefer because using the labels, I don't have to keep track of the numbers in my head. So now we do a usual thing, okay, LDIB with F underscore LVS, subtract that much from the stack pointer, and then we add it back later on before we go for the actual return code, which is LDB, comma D, increment D, and then JMPB, like so. So by the time we get here, the frame is fully constructed. So I will put a halt instruction here just so that I can see where the stack point is pointing to. Okay, so I will even comment here and say the frame of F is now set up. Okay, save the code and then we run it. So as River Spider is running it, I am going back to the map and basically complete its picture. So I would have reserved the next two locations for the local variable mine. So this is going to be f's mine dot pn. This is going to be f's mine dot pv because pv is the first member, it has a lower address. Pn is the second member, it has a higher address. So that's why it looks kind of confusing, but that's what it is supposed to look like here. And then the stack pointer, because it's already fully set up, so the stack pointer should point to the local variable. And now we're going to extend the coloring to these two rows too, because now the frame is fully constructed, like so. Okay, so this is what we're expecting to see. Okay, so from the perspective of the analysis tab, the only change is where the stack point is pointing to. It should be pointing to location F9. So now we go back to the trace and scroll down a little bit, and we see that, oh, okay, very good. The stack pointer is indeed pointing to location F9, so everything is working as expected at this point. Do we have any questions about this? Are we good? Okay, all right. So now we continue with this code. I'm looking at the clock. I think we probably have enough time to do it. All right. So it looks kind of messy right now, but it's not quite as messy as we might think it is. So we'll start with the first the first statement on line 15. So on line 15, on the right-hand side, we need to get to the value of member PV of the structure that is pointed to by prev, add one to it, and store it to the PV member of local variable mine, and that's all we need to do. Okay, so the ordering is everything. Okay, so what you need to do is to figure out, okay, what is the ordering of doing all this stuff? So the first thing we need to do on the right-hand side is to get a pref. So that's what we'll do. Okay, LDIA, or whatever register you want to use. We can use register A, B, or C, doesn't matter which one. So we get the offset into the register, and then we add to the base of the frame because I haven't pushed anything on the stack. The stack pointer points to the base of the frame. We have the address of pref now, but we need the actual value of pref, which is now a pointer to the structure that we need to point to. And then we need to get another register to tell me where do I find member PV in the struct X. Add those two together. So now register A is the address of member PV of the structure that pref is pointing to, but I need the value of that, so I need another dereference here. So now register A should be the value of member PV of the structure that pref is pointing to. Well, I think this is a good time to put a halt instruction here. And I also want to comment what register A should be at this point. So register A, okay, register A should be, um, let's see, member PV of the local variable of main is a 0. Okay, let me show you why I know that. Because it has to do with um, PV is, no, it's A, sorry, I take it back. I take that back. So this should be the address of A of main, which we know is 09, I think. Okay, let me just pause here. Does everybody understand what I wrote on line 30 in the comments and why I know that register A should be the address of the static local variable A of main? Because that's how I initialized the PV member of main underscore mine or mine. Yep, sure. So with this one here, because this is the first member, right? So the first member of, okay, let me see if I can do a V split on top of a vertical horizontal split. Split. Ah, nope. Okay, there we go. All right, so this is PV, the first member, and this is how we initialize it. And then later on, we pass the address of m mine to f. So that means pref is the address of m mine. So that means the PV member of what pref is pointing to should be the address of A, and A is our static local variable. So that means we now expect register A to be the address of the static local variable A of main, which is at location 09 the last time we checked. Okay, so this is important, okay? Because I'm not really just stopping in and take a look at things. I know what it should be, and I stop to check whether it is as I expect. Okay, so the exercise is not so much that, oh, we're just pausing a lot, okay? The exercise is knowing what the program should have accomplished at this point, and then cross-checking whether that's what we are seeing. Okay, so I can still miss a few things, so like I can miss details and whatnot, but we'll go ahead and give it a try. Okay, and this is already the trace. We're expecting register A to be updated to a value of 0A, 09 at this point, and it is not. Okay, it's 1C, but that could be because I shifted things around here because I put the definition of F on top of the static local variable. So I'm going to go back to the assemble tab and find out where is main A. So main A is indeed at the location 1C. So everything actually checks out at this point. Are we good so far? All right. So once again, I can be talking a little bit fast in the class, okay? So it is important that, okay, let me check, that we are recording and with the voice being recorded, okay? Because that's really crucial. All right. Yes. Yeah. The so if I were to put the halt instruction before line 28 or right after line 27, Then register A would be the address of member PV of the M mine local variable of main. But by dereferencing it, now we have the address. Yep. And in fact, you can check that too. Okay. So if you go back to the trace here, if you go back to the analysis tab, this is the last value. This is what it was before. So the question is FD the address of member PV of M mine of main? Okay, so that's the question. Now we go back here and we look up location FD. It is in fact the address of member PV of M mine, which is a local variable of main. Okay, so is that helping? Yep. hmm So this is the advantage of being able to trace the entire execution of the program because we can execute the program backwards. We know how we got here. All right, so let's continue. And on this side, we can quit one because we otherwise I don't have too much of a window. All right, so we switch back on this side. So we are now done with this, which means what is left is just to increment A. So we just add one to it, and now we have to assign it back to the PV member of mine, and mine is a local variable of the type struct X. So mine is not a pointer; it is a structure itself. So this is LDI. Which register can I use? Register B is fine. So this is going to be F underscore mine, which is the offset from the base of the frame to local variable mine. And then we have to add to it X underscore PV, which is the offset from the beginning of the structure to member PV. Add these two together. And then we have to add the stack pointer also, because otherwise all we have is an offset. We have to add the stack pointer, which is now pointing to the base of the frame. So register B now has the address of member PV of the structure mine. And all we need to do now is to do a store, and that should complete the operation. So once again, I'm going to put a halt instruction here. So you can see that I just wrote 3 lines of code, okay? But I'm going to double check. So what we should see here is mine.pv should now get, um, I think it is uh, the address of A of main, and then +1, which is which is really just literally +1 because it's an array of integers. So that would make it. We'll figure out where it's supposed to be because the locations would have shifted. Okay, so save, run it again. I hope these homework assignments helped you also with understanding C code a little bit better, because this is the kind of code that you will be encountering in CISP 400 and also 430. A lot of pointers, structures, and stuff like that. All right, so now we can go back to the trace, and then we look up the steps here, and we just store a 2-3 at location F9. So the question is that supposed to happen? Location F9 is the PV member of mine, so changing this location is indeed correct. But are we supposed to store the value of what again? 2, 3? So that really has to do with the question of where is static local variable A of main in this version. So now we have to go find A. This is the first location, and this is the second location. So everything is good. Okay. Are we still doing okay so far? Yes. Okay. All right. So we go back to the code. Okay. So we can now get rid of these 2 halt instructions. We are now done with the first line of code on line 15. Now we move on to line 16. So line 16 is a little bit easier, okay, because there's not a whole lot of stuff to do. So we do a LDIA with F underscore prev, add AD, LDAA. That's on my right-hand side. And then the left-hand side is kind of like the previous one, LDIB with F line. x underscore pn plus add bd, and then we just have to do a store ba. So that should accomplish the second line. Okay, but as usual, we're gonna have to put a halt instruction here. And we now have to say, okay, what are we supposed to see at this point? So mine dot pn should now be the same as prev. Okay, so that should be enough. We can look up on the stack to find out what it's supposed to be. Um, so save, run it. So the trick of actually adding comment to the halt instruction is helpful because when you get to the trace or the analysis tab, now it is actually showing here. So we are asking the question of, are we, oh, did I save the code before I ran it again? Did I forget? I might have forgotten. Oh, because I typed uppercase W instead of lowercase, so it wasn't actually saved. There we go. All right. There we go. We got a few more lines of code. And by the time we get to the halt instruction, we are asking, is local variable mine or the member pn is getting prev? So now we go back to the map here. We are now saying, okay, is this getting the value of prev, which is fd? In other words, we're supposed to see this fd here. So location fa should be updated to fd, and location fa is in fact updated to fd. So everything match. Okay. Do we have any questions about the approach of writing this program? No questions? Okay, all right. And we can move on. All right, so we are now done with line 15 and line 16. We are moving on to line 17 of the C code. So we are supposed to check what is pointed to by member PV of the local variable structure mine. Okay, so that's, we have to spell it out or articulate it. So that means we have to do a LDI a f underscore mine. And because mine is a structure already, I can directly add the offset to a member to the offset. And then we still have to add the stack pointer to register A because it is still a construct on the frame, which is on the stack. So now we have the address of that thing, and now we have that thing, which is the member, the value of member PV, but we also have to dereference it one more time, and then we check whether it is 0 or not by using AND AA. If it is not, then we go to the else branch, so we go to f underscore else 0. Otherwise, we are now in the then branch. This is f underscore else 0. We have to do the whatever the else branch is supposed to do. And the end of the then branch needs an unconditional branch to the end if label so that we can skip over the else branch. So this is once again the way I usually code is to write out the entire structure first before I do anything else. All right, so I just put in a control structure here, which means I just put in something that can check whether um, whether the PV member is a null or not. Um, so I can now put a halt instruction in each one. Okay, halt. This is the else case, and then halt. This is oops, not here, and here. This is the then case of the halt. Okay, so once I put these in, I am going to check. Okay, I will basically force the program to stop, and the way it is right now is which one should I stop at? In other words, what is the value of a PV of mine and what it points to at this point? Is it pointing to null or is it not pointing to null? Okay, so we know it is, as a pointer, it is not null, but is it pointing to a 0? So we already know in the code analysis, it's pointing to the second element of local variable, the static local variable A, which is -2, I think. So we know it's not null, so we should go to the then case. So that means that we should stop with at this halt instruction. So I'm going to run the program again. Okay, so let me save the code first, and then we'll run the code again, and we should stop at the halt instruction. And then the next time we're going to test it to make sure that it does stop at the halt instruction of the else by forcing it to go to that place. All right, so we go back to the trace, and it does stop at the then case, okay, or the then branch, which is exactly what it's supposed to do. And to make sure that the branching mechanism is working correctly, we can also now change the code in main so that we are not passing a over here. Instead, we are passing a plus 1. So if we are using a plus 1, that means, where is local variable a? Oh, it is right here. So if it is already here, then plus 1 would be pointing to the null, to the 0. So that means if I modify this code, then it should go to the else case. So now we go to main, and we just make that modification of the initialization of m mine, which is here, and then we increment b before we store. Okay, so I'm gonna have to remind myself that this is just for testing. Okay, to do remove after testing, save. Okay, so this time the program should stop at the else branch. Okay, because I just forced it to. Yep, so this time it did end at the else case. All right, I can see that I'm losing probably half the class easily at this point. But the point is, you have to think about how to test your code. And the way you derive a test plan to test the code at about this time, that is actually studying. It's not only studying for this class, because nobody cares about TTP ASM after this class. But being able to derive a test plan based on the C code is going to benefit every single class that has to do with high level programming language because it forces you to analyze, okay, how do I test whether this conditional statement is working correctly or not? So you have to reproduce the conditions to force the program to go on one branch or the other branch. That type of analysis is what you actually need to develop in order to, well, to get a job in the age of AI. It is critical thinking. Okay. So far so good. Okay, we just verified this is all working. So now I can remove the test code over here, go back to the halt instructions, and we can take out both of these halt instructions because they are in fact working correctly. All right, so we still got about 8 minutes. Do you guys want me to finish this or do you want to do something else? Finish it? Okay, let's do it. Let's do it. All right. So, we are pretty much at a home stretch now, because we just have like what, a few lines to do at this point. All right, so we go to the then branch, and it is a recursive call using the address of mine. Okay, so we do LDIA f underscore mine, that's the offset, add AD, that's the address, push that on the stack, decrement D, STDA, and then we push the return address, okay, LDIA dot 6 plus, decrement D, push it on the stack. Now we continue execution at the function that we're supposed to call, which turns out to be the same function that I'm in at this point. Increment D after we return to get rid of the only parameter on the stack. That should be the recursive call. The else case is a loop, okay? So every time I see a while loop, this is just what I would do, okay? Now, whether you want to program like this or not, that's up to you, okay? So this is the begin label, this is the end label, and then right before the end label, I need an unconditional branch back to the begin label. So this has to happen for every while loop. I might as well just put that in the first place. So now I go back and say, okay, so how do we get out of the loop? So the way we get out of the loop is when pref is null. So that means we do a LDI, A, F underscore pref, add AD, LDA, and AA, JMP, oh, JZI to F underscore and while zero end. And now we can get to the body of the loop, okay, which only has 2 lines. So should I just kind of go for it, or do you guys want me to debug it? Go for it. Go for it. Okay, I think we should just go for it. Okay. All right. So the right hand side here is whatever is pointed to by member PV of the structure the previous is pref is pointing to. Okay. So LDIA F underscore pref, that's the offset, that's the address, that's pref itself, which is the address of a structure. So LDIB with X underscore PV, that's the offset from the beginning of the structure to member PV of the same structure. Add those two. So now register A has the address of member PV of the structure that pref is pointing to. LDAA, it is now the value of the member. LDAA, now it is what the member is pointing to. So I did not write a single line of comment, which means that's something for you to do. Okay. The best thing is when you run this code, you can actually get to see how the value of register A changes in the trace, and then you can go back to um, the map that we drew earlier and actually figure out, okay, what is register A? It is the address of this member. What is register A now? It is the value of the member. What is register A? It is what the member is pointing to. Okay, so you can actually see everything in the trace. Okay, that's the value of the trace in this particular tool. And I just need to assign it to printer. That's actually pretty easy to do because printer is a global variable. So I just say printer as a label, stba. That should store to the global variable printer. And now we have line 26, the last line to uh, implement. So this one is ldia f underscore pref add ad. And I want to keep register A as the address of pref because I need that on the left-hand side too. So when I do a LD, I'm going to do a LDBA. Okay, so register B is pref, which is a pointer to a structure. I use another register C to store the offset to member PV, X underscore PN, um, add BC together. So register B is now the address of member PN of the structure that pref is pointing to, but I need the value of that. So I need a LDBB, and then we store that to whatever A is pointing to, because register A is still the address of pref. So we can store B to A at this point. That should complete the whole thing. Okay. So we'll see how this works. Okay, so if this works correctly, printer as a global variable should get exactly these values. Okay, it should update to 1, then it updates to -2, and then it should stop updating, and then the program should go back or unwind the stack back to the beginning. Okay, so we'll see. So we have to look up printer first to find out exactly where it is. So we just have to look up where is my printer. There we go. So printer is still at the address of 09. So this time I will be a little bit lazy and only look for updates at location 09. And that's only with column C. So I go to edit and go to find and replace. And what we are looking for would be location 09 is updated to something. And we are not replacing anything, we're just trying to find it. All right, so this is the first time we update. It updates to a content of 1, and then it updates to -2, and that should be the only 2 updates. So if I try to find again, it should wrap around. Yep, so it just wrapped around. So there are only 2 of those. Okay, so far so good. And then we can now check whether the program exited healthily. So we look all the way to the end. It is now at the correct halt instruction. The stack pointer is balanced. So as far as I can tell, everything is working. All right. And I definitely did not plan for this to happen, but it just so happens that we are right on time with 30 seconds to spare. Any questions? And the whole session is recorded, okay? So that's the thing. And I will upload the solution of this particular homework or program through the announcements. Yes. The FE can be an address, can also be a value, but we know the printer is printing -2, so the interpretation would be assigned interpretation of the bit pattern. So does that answer the question? Okay, all right. Any other questions about today's lecture? I'm not giving you guys another lab, okay? So you're good to go in terms of labs. I will stay here, if you have any questions, if you want me to take a look at your program, if you're trying to get it to work and you need to ask some questions. But otherwise, we are kind of done with all the labs. Okay, any questions? Yes. Hmm? How do we study for the final? Okay, very good. So the way you study for the final is being able to track the registers. Okay, that is the most important thing that you need to do is to go to the program that I have written so far, okay, and be able to associate the assembly code with the C code. So you should be able to point to one particular line, okay, whatever the line turns out to be, like this line over here, okay. So I point to line 74 of the assembly code, and you should be able to tell what is in register A after that instruction, and how does it correspond to the C side of the code. Okay, so we have to be able to identify, are we looking at the address of a member of a structure that is pointed to by prev? Are we looking at prev itself? Are we looking at the address of prev? Are we looking at the offset of prev from the base of a frame? Okay, so all of those are important. Okay, as long as you can track and understand how we use assembly code to implement the corresponding C code, that is what we want to achieve. Now, how do we get there is a different question. In other words, you ask, how do we study? I would say being able to comment this entire program is a starting point. You might be able to use Gemini to help you too, in terms of commenting, what each line is trying to do, because I think it understands enough to do a good portion of the work. Hmm? Yes. Um, no. So when I said systematic, I meant a systematic way to address or to do things during the final. So the studying part, there's no such thing as a critical systematic way because we all learn differently. But when you are in the exam, how do you check for those errors? Or how do you verify whether the code is correct or not? There is a systematic way to do it. So there are two separate things. One is studying, and the second one is how do we answer the questions or how do we find the problems of the code in the exam. So those two things are slightly different, but they are related. I'll just put it this way. You cannot do the second one without the first. Yeah, go ahead. Did you have a question? Yeah, yeah, both of them. I'll put it into a zip file and then upload the zip file. All right, so we'll focus on the assembly code first. So the studying part is really important. It's not about memorizing the sequences of code, okay? Because it's one, it is not possible. I don't think it's possible. Two, if I change the sequence of code just a little bit to achieve the same result, then you'll be lost, right? So you don't want that to happen. You really want to understand why the sequence of code works. What does it really do? How does it correspond to the C code? That is the most important part because there can be multiple sequences of code to get the same thing done. In other words, don't memorize. Okay, if you try to memorize, it's the wrong approach. Yep, you are allowed, an infinite amount of dead trees paper, during the exam. So now would be a good time to think about what do you want to put on those pieces of paper. So as you go through this, right, then you go like, okay, what do I need to track? What are some of the tricks? How do I differentiate between these two concepts if they seem confusing to you? Those are the things that you need to put onto the paper because you can bring any number of paper. Okay, you can say, oh, I only need one single sheet. That's fine. It's cool. If you want to say, I want to bring all the sample programs that we have gone through in class that has all of your comments in it, that's perfectly okay too. Not a problem. Okay, as long as you're not using an electronic tool during the exam, other than a calculator, which I don't think is going to be super helpful in this test, it's going to be fine. So as you study, that's when you start to jot down some notes and go like, okay, I think this is going to be useful because under stress, I might forget about this. So that's what you need to do is to kind of prepare for the final exam now. And we got about what 2 weeks from now the exam. Have I talked about when the exam was? Nope. Okay. So let's talk about that. All right, so the only thing you need to do is to look up, ARC final exam schedule because I just go by the schedule. And this is a daytime class. So we look up daytime class. It's a Tuesday, Thursday class starting at 9 a.m. So that would put our final exam on the Tuesday of December 16th, and the start time is 8 a.m. So don't forget 8 a.m. because our usual lecture time is what? Exactly. So the start time of the exam is 1 hour before the usual lecture time. And I think it is helpful to be here about 15 minutes before, just so that you have some time to settle down, go to the bathroom, and kind of review the material that you bring with you, double check that you have everything. So I'm just going to write this down here and then I'll put it onto the calendar. So this is this. eh, So I write this down on the board, but I'm also going to make sure that if I have not done so, I might have done that already, but I might. So this is what I'm going to do. I would put this in the class calendar if it's not already there. I suspect that I might have put it there already, but I cannot remember which class I have already put the final exam schedule into the calendar. All right, so we are looking at the 16th. So I have not put this on the calendar. So we'll put it here, CISP 310, final exam, and the start time is 8 a.m. End time is 10 a.m. So we have exactly 2 hours. Okay, so that means you might want to either look at the projector because I will project the time like the first two exams and also the time yourself. Okay, you'll make sure that you don't spend too much time on one particular thing. Um, and the location is the same classroom, which is 305 for this classroom. So there we go. We have it on the calendar now. And if you have not done so, you might want to consider using the calendar feed. How many people use the calendar feed from Canvas? Okay, same here. Okay, this is particularly really important for people with ADHD because if you put this onto your personal calendar, all of the homework assignments, all the due dates, all the exams, and everything that I put into this calendar will appear on your mobile device. So one quick glance on your mobile device, and oh, okay, we got homework due, or we have an exam coming up. It's really great for your future classes, not only this one. But it does put all your classes onto the calendar. So if you're taking one of those psychology classes where you have like something to do every 2 days, then your calendar will have all of those too. It's not selective. So there we go. I'm done with today's lecture. I will stay here, as I said, but you are welcome to go if you're really done and or you want to work on your program somewhere else. Okay, so that's perfectly okay with me. And I will see you all on Thursday.